For a long time, Mars at night has been treated as simple and predictable. When the sun sets, the surface cools, heat radiates back into space, temperatures fall, the atmosphere thins and settles. In this view, nothing meaningful is supposed to happen after dark. Night is just the absence of sunlight, a passive phase between two active days. The planet cools, waits, and resets. This explanation is tidy, intuitive, and comfortable. It mirrors what we expect from a cold, dry world with a weak atmosphere. Mars, in this picture, goes quiet at night. The processes that matter are assumed to stop or at least fade into insignificance. If something looks odd, it is usually written off as noise, dust, or instrument limits. Under this assumption, Mars after sunset is not a place where new energy appears. It is a place where energy simply leaks away. But that assumption does not fully match what Mars is doing. When we look carefully, the nights are not just passive cool-down periods. They show signs of activity that repeat, organize, and return. Mars's nights reveal active processes, not just leftover warmth. Patterns emerge that do not behave like simple decay. Instead of a steady drop, there are reversals. Instead of uniform cooling, some regions behave differently from their surroundings. These are not one-off anomalies. They appear again and again across seasons and locations. This suggests that Mars is not merely losing energy after sunset. Something is shaping how that energy moves, and possibly when it is released. The night side of Mars is not simply what remains after the day ends. It has its own dynamics, operating on a schedule that sunlight alone does not control. The first clear hint comes from measurements taken in darkness. Instruments detect nighttime spikes in atmospheric glow even when the surface below is cooling. At the same time, some regions show temperature behavior that reverses expectations, warming slightly when they should be cooling most efficiently. These effects are subtle but consistent. They appear at similar local times and return with the seasons. Importantly, they are structured. They are not random flickers or scattered noise. The glow follows patterns, and the temperature changes align with them. This is the moment where the simple explanation begins to strain. Cooling alone does not create organized brightening. Loss of heat does not explain heat briefly returning. To understand what is happening, any explanation has to meet three requirements. First, it must operate only at night, not as a leftover effect from the day. Second, it must repeat globally and seasonally, not depend on rare events. Third, it must leave measurable signatures, either in temperature or in the atmosphere itself. If a process fails one of these tests, it cannot explain what Mars is showing us after sunset. These constraints narrow the field sharply. They turn a vague mystery into a focused problem, one defined not by speculation, but by timing, repetition, and measurable change. The timing of these effects matters. They do not appear randomly through the night. They concentrate in a narrow window, beginning shortly after sunset and fading before dawn. This window becomes most pronounced during seasonal transitions, when Mars is shifting between warmer and colder periods. During these times, the atmosphere is already adjusting its structure and circulation. The night behavior seems to lock onto that instability. Outside this window, the signals weaken or disappear. This constraint is important because it tells us the process is not constant. It depends on the changing balance between sunlight, atmosphere, and surface. Whatever is happening waits for the sun to leave, then acts within a specific nighttime rhythm. That alone rules out many simple explanations. The standard explanation points to radiative cooling combined with dust-driven heat redistribution. Mars is dusty, and dust interacts strongly with infrared radiation. During the day, dust absorbs heat. At night, that heat is released back into the atmosphere, slowing the cooling process. Winds then spread this warmth unevenly across the planet. In this model, night anomalies are not new energy. They are delayed energy, stored during the day and released unevenly after sunset. This explanation fits much of what we know about the Martian climate. It is grounded in physics that we already use to model the planet. On paper, it sounds sufficient, but the details do not line up cleanly. Radiative cooling and dust transport are diffuse processes. They tend to smooth things out, not sharpen them. They struggle to explain localized nighttime brightening and structured atmospheric patterns. If heat were simply leaking back out, we would expect gradual transitions, not spikes. We would expect broad regions to behave similarly, not neighboring areas to diverge. Most importantly, this explanation does not naturally produce repeating nighttime glow patterns tied to specific local times. It explains the delay, but not the organization. It explains retention, but not apparent activation. That opens the door to a different possibility: nighttime chemical reactions in the upper atmosphere. Mars's atmosphere contains reactive gases that can combine after dark, producing faint light and releasing small amounts of energy. These reactions are known on other planets and even on Earth. At night, without sunlight breaking molecules apart, some reactions become more stable. This could explain the atmospheric glow and its structured appearance. It also fits the requirement of being strictly nocturnal. However, there is a problem. Most known reaction rates drop sharply without solar input. The energy released may simply be too weak to account for the observed thermal effects. The chemistry works in principle, but its strength may fall short. The difficulty with a purely chemical explanation is scale. While nighttime reactions can produce light, they are typically faint and energetically modest. On Mars, the upper atmosphere is thin, and collisions between molecules are relatively rare. Without sunlight to drive photochemical buildup during the day, the supply of reactive species is limited. This makes it hard for chemistry alone to account for repeated temperature reversals near the surface. The glow may be real, but the energy involved appears insufficient. It could explain why something is visible, but not why something feels active. Chemistry may be part of the picture, but by itself it struggles to move enough energy to shape nighttime behavior measurably. At this point, the question has to change. Instead of asking why Mars cools strangely at night, the better question is this: what process adds energy to Mars after dark instead of simply letting it escape? That shift matters. Cooling problems assume loss. This behavior suggests redistribution or delayed release. It suggests that energy is being stored, moved, and then reintroduced into the system on a schedule tied to nightfall. Once framed this way, the mystery stops being about missing heat. It becomes about timing, transport, and release. One explanation fits that reframing: coupled atmospheric tides. On Mars, the atmosphere responds strongly to daily heating cycles. As sunlight fades, large-scale pressure waves continue to move through the atmosphere. These tides can trap energy at certain altitudes and latitudes, then release it hours later. After dark, they can compress and expand atmospheric layers, generating localized heating and enhancing chemical glow at the same time. In this view, the glow and the temperature reversals are not separate mysteries. They are linked outcomes of the same process. The atmosphere is not calm at night. It is oscillating, shifting energy vertically and horizontally, and releasing it in structured ways long after the sun is gone. The challenge is proving it. Nighttime data from Mars is sparse. Most instruments favor daytime observation, and vertical measurements of the atmosphere are limited. We see hints, not full profiles. That makes it difficult to track tides directly from the surface to the upper atmosphere through the night. What we have are partial snapshots, enough to suggest a pattern, but not enough to close the case. Until continuous nighttime monitoring improves, this explanation remains the best fit, not a confirmed answer. Mars is telling us something after sunset. We just do not yet have enough night vision to hear it clearly. The most consistent explanation is not a single mechanism acting alone. The evidence points toward a hybrid system. Atmospheric tides provide the structure, the timing, and the ability to move energy after sunset. Nighttime chemistry responds to those shifts, lighting up regions where compression and release are strongest. Neither process fully explains the observations by itself. Together, they do. The tides organize the night. The chemistry makes parts of it visible. This combination satisfies the constraints. It operates only at night, repeats with seasons, and leaves measurable thermal and atmospheric signatures. It is not an exotic answer. It is a layered one. Mars is not doing one strange thing after dark. It is doing several ordinary things in an unusual alignment. When the sun leaves Mars, the planet quietly wakes up. No alarms sound. No surface glows brightly. Only slow waves moving through thin air, releasing what the day set in motion, long after the light is gone. Before we close, a quiet thank you to everyone supporting this channel. Your support allows this work to stay slow, focused, and independent. I'm genuinely grateful for it.